for this lab number 2, what we're going to do first is to look at resistances, reading the color codes. The next one is looking at a source of power, the EMF, the electromotive forces, checking voltage. Next step is looking at the diodes. We have only dealing with one diode here, so we'll be talking about that, especially the directions. And the very last step is drawing the schematic with all numerical values labeled. Once we finish, then we can answer the different questions. So the way to go to step number 4 is just to start off with all of the unknowns. So what are the unknowns? Resistance colors, resistance numerical values, the EMF, defining the type of diode, and then we do the schematics with the labels. Okay, so let's get started. I'm going to start with the reading the resistance, step number 1. Text says that we have numbered it from right to left, so this would be R1, R4. Violet is 7, express it as 4.7 kilo ohms. Number 2, red, or 2.2 kilo ohms. Tolerance 5%. Number 3 is brown. Brown is 1. Then we have a black. Black is 0. And then we go back to brown again. So plus or minus 5%. And the last resistor is, we see again here, this is the tolerance. If you want to keep all of these in terms of kilo ohms, so 1.5, 0.1, 2.2, 47 kilo ohms. Okay, so that's the first step on resistors. Next step is the EMF. So this is not very difficult to do. One information that may be also necessary is to look at 150 amps. So that means we can go over the 150 amps here. About the electrode, we have to, so let's say this is positive and this is negative. There should be some indication always on the battery to tell you which one is positive electrode, which one is negative electrode. So that's the four your information. If we have, for example, an electric circuit, and one is, here is the E, this is the epsilon, the electromotive force. So the longer plate is always the positive, and the shorter plate is the negative. And we have to connect this to the other part. Okay, so that's what all we need to know about the electromotive force. So it's 12 volt. Now number 3 about the diode. So if we have to draw it in the here's the wire, here's the electric circuit. So it is always from the positive to the negative. So you can draw it this way: positive, negative. So if you have, for example, on this side is the EMF positive, on this side is attached the EMF negative, and then the current will pass through positive, positive, negative, negative. So the current will pass through, have a current passing through here. So that means on the opposite direction, the current will not pass, the current is not passing in this direction. The other thing that we need to know also is the type of diode. If the diode is germanium, Ge, and then this has a volt drop of 3.03 volt. We have to take care of this, 0.3 volt. So that means this is acting just like a resistor. If the current is passing through, this is acting as a resistor in this direction with a 0.3 volt drop. If it is a silicon, and if the diode is made of silicon, then the drop is 0.7 volt. The drop is 0.7 volt. Let's do the schematics with the numerical values. This is what we had. The first set is in a series. This is the ground. This is the ground, so let's call this G. This node is C, this is B, and this node is A. Then we have here a switch, and which is very important to know here is that we have the electromotive force here. Make sure that you see the positive. The positive is down here, the long plate. The negative is up here. It's very important. And the last thing is the diode. So we have a diode drawn in this direction. So what you have to do is just to look at, so it is a silicon. This is a silicon. Anyway, that won't change anything because I'm going to show you in a few minutes why that. So let's put numerical values of the resistor. So this one is 47 kilo ohms, R1. R2 is 2.2 kilo ohms. R3 is 0.1, same unit, using the same units. This is 0.10 kilo ohms. And R4, this is 1.5 kilo ohms. And this one, the last one here is the R3 again, 0.10 kilo ohms. And then let's put the last thing here. The E0 is 12 volts. So now we have the entire circuit. So the next part is just to answer all of the question and studying this the circuit here, which is important to set it up correctly as it is, especially in this part. Now, the way I said the silicon, it doesn't matter if silicon or germanium, because just looking at the schematic, you see that the current is always, once you close the switch, the current is moving from the positive sign. So that's the direction of the current. And I would say that sub-node, principal current, there is nothing going up here. Why? Because you see the negative sign. The negative of the diode is in connections with the positive of the electromotive force. So no current is passing through. So we just ignore it. So it doesn't matter if it's a silicon or germanium, just ignore it. So the current is moving in this direction, splitting into here, moving back here again, the I0 principal splitting up in two directions, and you go back on the node A, going back to the negative of the electromotive force. Okay, so the next step is we're going to do the study of this circuit. Okay, so for this second part of lab 2, we just applied the rules. Here is the schematics. Let's do the analysis quickly. So we have two resistors in parallel, and then one resistor in series. The diode is in opposite direction, if you say that, of the electric current, of the source of power, the EMF, electromotive force. So looking here, positive, so that means the current should go in this direction. Now, this is negative. If you look at the diode, negative is attached to the positive current here, so that means there is no current passing through. This will be forbidden. There is no connectivity in this case. So there is no current passing through here. There is no current passing through. So the reason is, again, that to have a diode working, or what you call the on diode, on should have the positive related to positive, but this is not positive, this is negative. So we can disregard this circuit, so we can say that the principal electric current, I sub node, would just go through the bottom and going up, splitting into part here, electric current here. I will call this one I1 and I2. And then we can see it again here, I sub node, and splitting into parts, then combining again here, closing our circuit. what do we need to know? We have just to apply the basic rules. The first one is Ohm's law. So what is again Ohm's law? If you have a V voltage, V equals resistance multiplied by electric current. And from this equation here, we can have R or I, etc. And that's all. So the second part is we apply the rules for R equi for parallels, R equi for series, and if you have a mixture as well. One of the question is, again, we are not talking about the diode, but if we had the diode, the silicon, and if it was one, then we would take care of the drop of 0.7 volt. The diode is in the wrong direction, if I could say that. It is just off. And the last thing is about power. Power is voltage times the principal current, or if we do not have voltage but the resistor equivalent, we can multiply this by R square, so we can use either one. And the last thing is about the total energy of the circuit. So total energy is, we can express it at watt hour or watt per second. If it is watt per second, then we can use, in this case, the unit joules. So that's what we have to apply. So let's see. If you have to do the answer the question number 1, what is the R equivalent for R1, which is in parallel with R2? So again, I'll just give you the answers. 2.1 kilo ohms. Question number 2, what would be the R equivalent if we have R3 versus R4? Case we have 10.7 kilo ohms. 10.7 kilo ohms. Question number 3, what is the R equivalent for the entire circuit? What you have to do in this case is just to take 1 plus 2 plus 12.9 kilo ohms. Question number 4, what is the principal current? I0. So we just use Ohm's law, so that will be voltage V divided by Req, the resistance equivalent of the whole circuit, 0.93 milliamperes. There is one thing that you may think about. In doing such a calculation, if you have a kilo ohms, you can make it with milliamps. Don't do any conversion between those two to keep a voltage. Okay, question number 5. You have to calculate the drop of the voltage of VA between the nodes A and B. So we can again use Ohm's law, V equals RI. So we have already I, the current doesn't change. The R would be R. This would be from number 1, the equivalent. That gives us 1.95 volt. Question number 6. What is the VBC, the drop between node B and node C? We calculated the equivalence in question number 2. So we just multiply answer for question number 2 by the I0. That will give us 9.95 volt. Number 7 is a VCG. We can just reduce the 12 volt minus 9.95, then that will give us 0.1 volt. Number 8, what is the power? So just use P equals UI. You have the U, 12 volt. You have I, 0.93 amps minus 3. If you keep it as milliamps, then we're going to get milliwatts. So that gives us 11.2 milliwatts or 0.0112 watts. And the last question, 9, what is the total energy? Just multiply the power by the time. If we run it in 45 minutes, then that will give us 30 joules in 45 minutes. So multiply by seconds, convert the 45 minutes into seconds, then multiply by the power, number 8, then you get your energy of the electric circuit. In the real world, it is used most of the time as watt hours, but we're going to use just the joules, the total energy in joules, 30 joules.